Every year in December, a bunch of programmers come together online and try to solve the same series of 25 coding exercises in an event called Advent of Code. Some try to be the first to solve a problem, gaining points and shining in the leaderboard, and some are a little more chill about it and use it to learn a new programming language. When I do it, I use it to teach Rust. Last December, I wrote 16 articles going from the basics of error handling to parsing with the DOM crate, doing memory profiling, generators, and even creating graphical interfaces, compiling the result to WebAssembly, and embedding it on a web page. But the problems were getting harder and harder, and I wasn't getting any smarter. I was spending more and more time debugging silly off-by-one errors, or having to learn more maths than I'd signed up for, and since the focus of the series was Rust, and not showing off what a clever boy I am, I switched gears. For day 17, live on stream, I ported someone else's solution from Python to Rust. The result was about what you'd expect. A naive 1.1 Rust translation ended up being 44 times faster than the original Python. Adding an extra data structure and switching to a hash function that's faster for integers ended up making it over 2,000 times faster than the original, reducing runtime from 6 seconds to under 3 milliseconds. You could make some of the same changes to the Python version, or even switch to a different Python implementation altogether, and that might help narrow the performance gap, but it was never a fair fight to begin with. CPython, the main Python implementation, is just an interpreter. It reads the code, translates it to bytecode, and then at runtime it just steps through the bytecode, interpreting it as it goes along. PyPy, however, has a JIT, a just-in-time compiler, which is able to translate bytecode to machine code, and the result can be run directly on the CPU with tons of air quotes for the pedants in my comment section. If you look at the computer language benchmarks game, where everyone is trying to prove their language is the fastest, for the n-body program, a math-heavy problem, the fastest solution is currently Rust, and then a JavaScript solution running on Node.js is only 8 times slower. Part of the reason is that V8, the JavaScript engine that powers Node.js, has a very good JIT. Even though variables in JavaScript are not statically typed, now it's a number, now it's a string, and now it's an object, the JIT is able to monitor what arguments functions are called with at runtime, and then make guesses. It goes, I'm going to generate code for this add function as if the arguments were always integers. And if that's the case all the time, if the guess was right, then things get really fast. But if the function gets called with an argument that isn't an integer, first you need to do the right thing. You can't add two strings, but you can concatenate them, and that's the same operator in JavaScript. And second, if that happens a lot, then your guess was wrong, and you might need to de-optimize the function and come up with another machine code version of it that branches on the type of the arguments. This is, believe it or not what today's video is about. But if I got you all curious about it, you can go read the article Speculation in JavaScript Core on the WebKit blog, which goes into a lot more detail. I felt pretty stupid while reading it, and I wish you the exact same. That just means you found something you can learn about. So Python v Rust was never a fair fight, because the languages are just too different. C++, however, is a language that's strongly typed, despite its C heritage, compiled ahead of time, and used in performance-intensive scenarios. They used to make game engines and browser engines and databases. It's got to go fast. So, on day 18, when I ported a solution from C++ to Rust, I didn't know what to expect. It could be faster, it could be slower. It was slower. Much slower, in fact. I was a bit sad until I realized it wasn't slower at doing the heavy computation required by the problem. It was slower because it was doing a bunch of unbuffered writes to a file at the very beginning of the program. In the original solution, just to make sure that the puzzle input was parsed correctly, the author had the program write everything that was parsed back to a file so that they could look at it and go, yeah, that looks okay. And they used C APIs like fopen and fprintf, which are doing buffering. At first, it's writing the text to some buffer in memory, and then when the buffer is full, it issues a write syscall, which is how you politely ask the kernel to perform some I/O, and that's a lot more expensive than writing to memory. But in Rust, I was using just a file, so each individual print would issue one write syscall, and that ended up taking something like 20 milliseconds, whereas the C++ version was done in 9 milliseconds. Once I wrapped the file in a buff writer, I discovered that the part 1 solution, there's always two parts, was 1.5 times faster in Rust than in C++. We went from 8.9 milliseconds to 6.1 milliseconds. For part 2 of day 18, the story was much the same. The naive 1.1 Rust translation was already 50% faster than the original, and then by switching to a different data structure, changing the hashing function, and targeting modern CPU instruction sets, it became more than 3.5 times faster. For it to be really fair, you would need a C++ expert, which I'm not at all, to make similar changes to the C++ version of the code, and the gap would probably narrow significantly. But what's interesting to me is that the Rust version used less syntax, and it was very easy to make those changes and bring it down from 8.5 milliseconds to 3.3 milliseconds. I am biased, of course, since I know more Rust than C++, but in C++, I had a hard time even embedding the input into the executable for benchmarking. I discovered that C++ had raw string literal syntax, but that it had parentheses instead of the double quotes. And then MSVC, Microsoft C++ compiler, choked on the literal because it was too large. So I ended up using XXD to generate a header file, and then had to figure out the proper way to include that from C++ sources, running into a bunch of template instantiation errors, which turned out to be a missing cast or a missing include. I've never missed Rust diagnostics as much as I did then. The operator overload syntax in C++ seems hard to remember, and I say that because the original had a link to a Stack Overflow answer about how to do operator overloading. And Rust is just implementing a trait like any other, except we didn't even need to do that because we were able to derive it with a simple attribute. Finally, iterators in C++ are very different from Rust iterators. The pattern they use to iterate over a set, removing some elements but keeping others, got me worried, but it turns out that that's just what the retain method does in Rust. Another part of the C++ code calls begin on a set, which gives you an iterator to the beginning of the set, as you cannot really tell from the name, and then it immediately dereferences it. In Rust, I had to call the first function, which gives you a reference to the first element, but in an option, because what if the set is empty? So in Rust, I just used unwrap, so that if the set was empty, it would print an error message and safely exit the app. But in C++, if you dereference the iterator returned by begin on an empty set, that's undefined behavior. You know, nasal demons, the thing that can steal your dog and optimize your whole program away. UB is bad. Don't do it. Anyway, the next day I thought, you know what? Maybe Rust being faster than C++ was a fluke. I'd like to try on a different solution just to make sure. And sure enough, on day 19, after porting a solution from that same person in C++ to Rust, it was slower, 20% slower. C++ ran in 4.5 seconds and Rust in 5.4 seconds. And this time around, it wasn't spending any time doing syscalls. It was just doing a lot of recursion, a function calling itself over and over. And I had no idea where to look. We used call grind, but that just took forever. We used not perf, which is like perf, except not. It's a sampling profiler. And it showed that, yeah, the function calls itself a bunch of times recursively, over 1 billion times actually. People pointed out that this solution was doing a lot more work than needed, and I could just switch to a better solution, but I decided to focus on figuring out why essentially the same code was slower in Rust than it was in C++. And it took me a hot minute. We disassembled both solutions with objdump, looked at them side by side, and it was pretty hard to make sense of it beyond the first few lines. So we used Ghidra, which can decompile to C, and started renaming registers after what they were used for. This all happened live on stream, and it lasted over 3 hours if you want to see the play-by-play. And finally, I noticed something funny. And we're not going to look at the actual code for day 19. We're going to look at simpler reproduction cases because I want this video to be accessible to people who don't speak x86 assembly fluently. So we need to build this up a little. Let's start simple. Say we're making a function that adds 2 64-bit integers. This is what the Rust code for it could look like. When compiling this code, Rust C will generate LLVM IR, intermediate representation. LLVM will generate machine code, and we can translate that back to assembly, which is closest to what the CPU actually does, but still human readable if we try hard enough. We'll be using Compiler Explorer, a free online service maintained by Matt Godbolt, whom you can support financially on GitHub sponsors, Patreon, and PayPal. Let's first look at the disassembly of an unoptimized version of add numbers with overflow checks disabled. There's 3 places we can put stuff. The heap, which can grow very large, but is expensive because we go through an allocator. The stack, which is limited in size, but very fast because we're just moving the stack pointer down to grow and up to shrink it, depending on the platform. And registers, which are very fast global variables directly in the CPU. There are exceptions, but as a rule, let's assume that if we want our code to go fast, we should try and use registers as much as possible. When we call a function, we are jumping to the start of its code, but before we do, we must put its arguments somewhere. If we can put them in registers, we should do that. And that's what's happening here. In main, we move 1111 to the EDI register and 2222 to the ESI register, then add numbers gets called. Call is almost like jump, except it first pushes the return address on the stack so we know where to continue execution after the function has returned. And in add numbers, we can see that the value in RDI, which is another name for EDI, is moved to racks, and then the value in RSI is added to racks, and then we return. A calling convention is where and how we pass arguments to a function. What can we say about the calling convention for this function? Well, it follows the standard x86-64 sysv API, which says if the arguments look like numbers, pass the first one in RDI, the second one in RSI, and then RDX, RCX, R8, R9, and that's it. So argument x is in RDI, argument y is in RSI, and the return value is in RAX. So far, so good. Now, let's look at the assembly for the optimized build of the same code. The code for main is the same, but the code for add numbers has changed. Instead of using a move to copy the first argument to RAX and then an add to add the second, it does both at the same time using lia. What are those square brackets? Well, if you have move RAX RDI, it copies the value in the RDI register to the RAX register. But if you have move RAX brackets RDI, it treats RDI as an address and copies whatever is at that address to RAX. This is useful if RDI is a pointer to the stack, for example. But in those square brackets, we can have more complicated expressions. If we have move RAX brackets RDI plus RSI, it would add RDI and RSI, treat this as an address, and then read whatever's there and then copy it to RAX. This would work if RDI was a pointer and RSI was an offset. This happens when reading struct fields, for example. As for lia, it's a bit like move, except it doesn't read whatever is at that address. It just copies the address itself, hence load effective address. So what's happening here is it's using a mechanism meant for computing addresses to do basic arithmetic, which is a very common pattern. Moving on, what happens if we add more parameters? Then it uses all 6 registers we can use for integer arguments: RDI, RSI, RDX, RCX, R8, R9. The unoptimized version moves the first argument to RAX and then adds all the other arguments, accumulating into RAX. And can you guess what the optimized version will do? That's right. Much the same, except it adds the first 2 arguments into RAX with lia. Could we do better than this? Probably, but let's move on. What happens if we add 8 numbers together? Then the last 2 arguments spill onto the stack. We can tell because it uses the same square bracket syntax to read from RSP, the stack pointer, plus some offset. Let's keep going. What if instead we pass 2 structs, each having 2 fields? Even without optimizations, we can see from add numbers disassembly that all 4 numbers are passed through registers. Main looks inefficient though. It's allocating space on the stack, moving all our constants there, and then moving them back into registers to call add numbers. Turning on optimizations gets rid of that nonsense, moving the constants directly into the relevant registers. And now, what happens if we have 3 fields per struct, adding 6 numbers together in total? Stuff gets weird. Real weird. So far we've dealt with 64-bit wide registers, RDI, RSI, etc. But we have wider registers. XMM0 and XMM1 are 128-bit wide. And you know what that means. We can pack 2 64-bit integers in there, 2 quad words, making a word 16 bits apparently. These are SIMD registers, SIMD for single instruction, multiple data. And that comes in handy. Let's look at the optimized code and try to go through it. There's a bunch of scary SIMD instructions in there, but the first thing that jumps out is that it's reading memory RSI and RDI points to. I can tell because there's move instructions with the source operand in square brackets. The first move, for example, moves 64 bits worth of data from wherever RSI points to the RAX register. The move DQU that follows does the same, using RDI as an address and moving 2 64-bit values, 2 quad words, the instruction stands for move double quad word on a line, into the XMM0 register. Let's follow what the function does step by step with diagrams. So originally both structs are somewhere in memory, each field 64 bits. RDI points to X and RSI points to Y. The first move copies the first field of Y, YA, to RAX. Then XA and XB are moved in one instruction to XMM0. Then YB and YC are moved in one instruction to XMM1, thanks to that +8 offset here, skipping over the 8 bytes or 64 bits of the YA field. P_add_Q, add packed quad word integers, adds both quad words from XMM0 into XMM1. That's 2 additions with a single instruction, multiple data. P_shuff_D, shuffle packed double words, is the most complicated instruction here. It has a destination operand, a source operand, and a third operand that defines the order. It's a series of 4 2-bit integers that define which double words to copy from the source to the destination. Here, the order operand is decimal 238, which in binary is 11101110. If we translate that to 4 decimal numbers, we get 3232, and that corresponds to the higher and lower 32 bits of YB plus XA, which is currently in XMM1. So all it's really doing is copying YB plus XA from XMM1 to both halves of XMM0. Then we have another pad queue doing 2 additions between both pairs of quad words. We only care about one of the results, so this could be an add, but the other operand is already in XMM1, so this saves us a trip. After that, we move the result we care about out of XMM0 into RCX, add XC at address REI plus 16 to racks, and add RCX, the result of all those SIMD additions, to racks, which gives us our final sum and return value. Easy, am I right? Aren't you glad you clicked on this video? But let's forget about SIMD stuff for now, possibly forever. One thing that's interesting is that this code passes 6 quad words to a function, and it uses 6 registers to do so. But as soon as we switched over to 2 structs with 3 fields each, it stopped using registers and started passing them on the stack. In some cases, that can be slower, and that's exactly why the day 19 solution was slower in Rust than in C++. Kind of. The day 19 solution was passing more integers, but they were 32-bit. The Rust compiler looked at it and went, you know what, that's too many numbers, let's just pass them on the stack. Whereas the C++ compiler, also backed by LLVM, looked at it and went, I bet I can pack 2 32-bit values in each of those 64-bit registers. And so we just use registers for everything. The reason this happened is really complicated, and I'm not going to get into it here. It is the kind of issue where you fix one case and that causes performance regressions in a lot of other cases. It's been an ongoing fight for years according to sources who are very tired. Okay, this is not part of the script, but I wanted to explain. So for functions that are not exported, that are not part of a public interface for a library, you can't call them from the outside, so you don't have to adhere to a known calling convention, right? You can do whatever you want. And so instead of using registers like RDI through R9, you could use 13 different registers. You could use XMM0 as part of your own internal calling convention, and that's what LLVM is supposed to do. But it doesn't, for some reason. And the problem is if you do that, you have fewer registers you can use in the callee, in the code that's calling the function. You might already be using those registers to just have local variables. Instead of allocating them in the stack, you have them in registers because you have those. But if you're calling a function that has an internal specific ABI that uses more registers, then you can use fewer in your callee, in the function that is calling the other function. And so that means that you now need to not use the registers for locals, you need to put locals on the stack, and that can get slower. So the reason is, it depends. It depends on what the callee is doing. You can't tell just from the function signature, and that's why it's a bug that's so hard to fix. There's not one good option for like which calling convention to use internally. So there you go. Does this story have a happy ending for Rust though? For the day 19 problem, slapping an extern C on the function did make it use registers for argument passing, and the compiled Rust code finally became slightly faster than the C++ version. But that was a coincidence. It's not a real generalized fix. It would depend on the target architecture, among other things. This works on x86 64 with this version of the compiler. Anyway, before I leave you, I want to show you one more thing. So we've seen that with the current version of the nightly Rust compiler, passing 2 structs with 3 fields each uses the stack instead of registers. And as I was discussing this with a friend, a thought occurred. 3 fields is an odd number of fields. Not just weird, also not even. So maybe something somewhere in the compiler doesn't like odd numbers. What if we passed 3 structs with 2 fields each? That's still 6 total. Would it still use the stack? Nope. It uses registers. And I guess this is my long way of saying, if you see a compiler engineer in the wild, ask if they need a hug. So, funny story, I checked my inbox today and it had a pitch for a sponsored segment for the video. I was like, heck yeah, I want all that money. And the email was from my cat. So here you go, the video is sponsored by Cat. Cats are very good. They're fluffy. That one sleeps a lot, so he's a very quiet colleague. I don't really have any complaints. It's not helping much, but I'm a self-driven individual in this tech industry climate, so that's good. Cat would like pets. I'm assuming that's Cat's way of saying he doesn't get enough. I don't know. I'm just reading from the pitch here. Cat also wants food. Not cat food. Cat wants human food. The thing that smells delicious in the kitchen, and that's what cat wants. And cat wants you to know that cat wants that. So yeah. Check out cats. This is just half my cats. I have double the cats that are shown here on the camera. And yeah. Cats rock. There's no discount code or anything. You can't use code fast online with cat. Just kind of have them and then pet them and then feed them. There's a bunch of cleanup, but you'll see when you get to it.